I'm going to try this quick check number 2, try to explain it, because some people seem like they're having a little trouble. So what we're talking about here is the idea that if we had some acid, and notice that this is a weak acid, and we're going to neutralize it with a base and put the resulting solution here into this other beaker, then we want to, so what is the pH of that neutralized solution? Now if this were a strong acid like HCl and a strong base like KOH, then we would expect the pH to be 7, but that's not the case in this case here. So we start off, first question is calculate the pH of the first beaker. So just if we have a solution of HF, what is the pH of that solution? And to do that, we have to do an icebox problem, and we need to know the Ka of the HF, and we're given that. And we're also given that there's 100 milliliters of this, and we really don't need to know that information for what we're doing. So this is a standard icebox problem. If we have 0.2 molar HF, the equilibrium is HF breaks up to be H plus and F minus. And initially we're going to say we have none of that. We're going to say X amount of HF dissociates. So if X dissociates, we end up with X H plus and X F minus. So at equilibrium, we would have X and X, and we'd have 0.200 minus X here. Now we can take these values and put them into our Ka expression, and our Ka expression is H plus F minus over HF. We have the value for that, and we would have X times X all over 0.200 minus X, and that equals 7.2 times 10 to the negative 4. But as we've been working through this, we realize that that X here is pretty small compared to our value of 0.2. So if we were being very official, we would say assume that X is much smaller than 0.200. So therefore 0.200 minus X is really about the same as 0.200. So we just make the simplifying assumption, X squared over 0.200 is equal to 7.2 times 10 to the negative 4. That would mean that X squared is equal to 1.44 times 10 to the negative 4. And we really want our value of X, which would be the square root of X squared, which is going to be the square root of 1.44 times 10 to the negative 4. And that value is 1.2 times 10 to the negative 2. And that is X. And we can see that our X is our H plus concentration. So if I take the negative log of this value, that will be my pH. And if we just do that, we get 1.92, two significant figure answer. So that is my answer for part 1. The pH of the weak acid solution just by itself is 1.92. Question 2. If this acid were titrated with KOH, would the resulting solution be acidic, basic, or neutral? Well, we're taking a weak acid, HF, and we're mixing it with a strong base, KOH. And the answer is it's going to be basic. And the reason it's going to be basic is after we neutralize, we're going to have a solution that has water, and it has KF, that's salt. Now the KF, we really don't care about the K. That's going to be a spectator ion. The K is going to go out of here, K is out of here. But we're going to have that F minus solution. And that F minus is the conjugate base of the weak acid HF, and that is going to make the solution basic. So when we do our titration curve, we're going to find out that the inflection point, the end point, is going to happen somewhere above pH of 7. Now we want to go back and say, well, how much of our base are we going to need to add? So here's our sample, and now we do need to know that we have 100 milliliters of this solution. And what we want to do is we want to calculate how much of our KOH are we going to need. Now we have 100 milliliters, that's not the number we're going to use. So we're just going to do the simple formula that the volume times the molarity of the acid equals the volume times the molarity of the base. And in this case, the acid is HF, the base is KOH. And since it's one H in HF and one OH in KOH, then we can just use this formula as is. And we can see what's going to happen. We're going to have 100 milliliters times 0.2 molar acid equals X milliliters times 0.3 molar. Not quite enough room here. And when we calculate that out, we find out we need 66.67 milliliters of the base. And that's not surprising. The base is a little more concentrated than the acid, so to neutralize 100 milliliters, we're going to need a little less than 100 milliliters. So far, so good. Now, for part 4, this is the thinking part. It says the neutralization of HF is poured, the neutralized solution is poured into the third beaker. So how many moles of F minus? The F minus is what is going to change the pH of that neutralized solution. So even though it's neutralized, it is not going to be pH 7 because it's a solution with the conjugate base of the weak acid HF. So how many moles of F minus? So here's what I want you to think about, is when we started, we had a bunch of weak acid, HA, and that's our generic version for an acid, because A stands for the anion. So in this case, the A would really be an F. These are a bunch of HFs. But as we neutralize, we add OHs to that, then we're going to turn them into waters, and they're all going to end up as A minuses. So all the H pluses form waters, and all our HAs end up as A minuses. Or in this case, all of our HFs are going to end up as F minuses. So if I want to know how many moles of F minus, what I really need to know is how many moles of HA did I have in the first place. So we know that we had 100 milliliters, which is 0.100 liters of our acid, and it was 0.2 molar. That's a 2. So volume times molarity gives me my moles. And so we can see that what we're going to have is 0.0200 moles of F minus. Now officially that is the moles of the HF, but that is also the moles of the F minus in our solution. So this is 0.0200 moles. Now we want to keep that in mind, that the volume times the molarity of our original acid will give us the moles of our negative ion. We're going to use that all the time. Now, what's the total volume? Okay, total volume. We had 67 milliliters from our base solution, but we have to add that to our 100 milliliters of the acid solution. So here we're going to have 167 milliliters of total solution, which we're going to use that as liters in a moment. Because the next part here is, what is the F minus concentration? Well, the F minus concentration in our third beaker, when we're all done, is going to be the number of moles of F minus divided by the total volume, but we do moles per liter, so that's going to be 0.1667 liters of solution. So when we get done, we have 0.119976 molar F minus, and because of the numbers we have, that's too many significant figures, we can round that off to 0.12 molar F minus, and that's an important idea. Now, for part 5 is calculate the pH of the solution in that third beaker. So why is that pH not even 7? Because we can have a solution where there's a lot of our negative ion, our conjugate base of the weak acid. So we're doing a problem where it says if I had a solution where the solution was 0.12 molar in F minus, what is the pH of that solution? So we're back to an icebox. So this one here is 0.12 molar. We don't care about the water because it's a liquid, and it's 0 and 0. And now we can kind of see this is going to be a standard sort of an icebox. 0.12 minus x. Now, this is the conjugate base of our weak acid, HF. So we have to get a Kb for this equilibrium, and we know the Ka was 7.2 times 10 to the minus 4, so we can calculate the Kb by using Kw over Ka. So the Kb for this reaction is 1.39 times 10 to the minus 11. Probably really ought to only be two significant figures, but I don't want to round off too early. Now, this is a very small number, so we can see that that x is definitely going to be ignorable. So we're just going to go on with our problem. So the Kb is the concentration of HF OH minus over F minus. And that equals 1.39 times 10 to the negative 11. And we'll just finish up our problem. So this is x squared over 0.12 minus x. But that x is going to be very, very small. So that's the same thing as x squared over 0.12. And that equals 1.39 times 10 to the negative 11. Now continue with our problem. So x is equal to the square root of x squared, which is equal to the square root of 0.12 times 1.39 times 10 to the negative 11. And that is going to be the square root of 1.668 times 10 to the negative 12, which is going to be 1.29 times 10 to the negative 6. Now that is what x, now x, we have to go way back and remind ourselves that x is the hydroxide ion concentration. So when I take the negative log of this value, that's going to be my POH, negative log, which is 5.8889, so 5.89, and my pH is 14 minus the POH, which I get 8.11. And I'm going to leave that with 2 decimal points, 2 significant figures. So when my solution is done, I'm not surprised that the pH is a little bit higher than 7 because it is a solution of the weak conjugate base, the conjugate base of my weak acid. And that's how we do these problems.